Hello everyone, this is chapter 4.3, which is entitled How Derivatives Affect the Shape of a Graph. And here we'll be talking about essentially using calculus to figure out what the graph will look like without actually graphing. In other words, we'll basically be using calculus to eventually sketch the curve of a graph, which is actually pretty helpful. In fact, we'll see a lot of specific details of curvature of a graph. And the first thing is what we want to take a look at would be intervals of increase or decrease. So here I explain what it means for a function to be increasing or decreasing. And I say if you have two x values, one smaller than the other, of course, in the domain of f, if f of the smaller one is less than f of the larger one, then the function is called increasing. However, if it's the other way around, where f of the smaller value is now larger than f of the larger value, then it is called decreasing. And I want to show you just by visualization. So just to give you kind of an idea here, let's imagine we have this curve f, and there of course is a local max and local min here and here, respectively. And what I want to do is I want to kind of separate the domain here into these three sections. I just want to talk real quickly about what's going on. So as x is changing from left to right, the function is going up, meaning for any 2 points in this interval, if you take f of those values, a larger one will have a larger f value. So here this is increasing. But really the more visual way of seeing it is as you go from left to right, does it go up or does it go down? So here then it would be decreasing, and then here it would be increasing. Okay, good. Now the actual important part where calculus plays a role here is when you start to consider the slope of the tangent line. Because of course, slope of tangent line is derivative, so tangent lines are kind of pinnacle, so to speak, when it comes to, well, calculus. So what I'm going to do is I'm going to pick any point in this interval where it's increasing and take a look at its tangent line. And we can do the same where it's decreasing, for instance. And where it changes from increasing to decreasing, we can even graph that one. So I have these three intersecting lines, and what you'll notice is that with this one that corresponds to where the graph is increasing, notice the slope is positive. Similarly, where it's decreasing, the slope is negative. And of course, we've seen before, where it's horizontal, the slope is 0. Okay, good. And in fact, we've also seen that just because there's a max or min doesn't necessarily mean it has a horizontal tangent line. It could have technically a vertical one. But even then, in that case, let me just kind of show you with the visualization down here. Let's say you had a max like this. It still changes from increasing to decreasing, actually, regardless of if it's a sharp point or a smooth point. So something to keep in mind. So there are two things we've kind of learned from this. And the first thing, let me write over here, is that the function is increasing when f prime of x is bigger than 0. The function is decreasing when f prime of x is less than 0. In fact, this is what is known typically as the increasing-decreasing test. To find intervals of increase-decrease, you solve these inequalities. The first inequality will solve the interval of increase, and the second inequality will solve the interval of decrease. We'll actually see examples of that, but I want to get a lot of this lingo out of the way first before we get into an example. And in fact, I want to do an example that'll kind of target a lot of different ideas at once instead of seeing little examples at a time. Okay, now I have some important start notes here. First, the local max is where the function changes from increasing to decreasing, which makes sense because, like I said, if it changes from increase to decrease, you pass the highest point. Similarly, you can say, well, the local minimum then is where the function changes from decreasing to increasing, which also makes sense. Because again, if you change from going down to going back up, you've passed the lowest point. Good. And with these two ideas in mind comes what is known as the first derivative test. Okay, so the first derivative test says if you have a critical number, remember critical number is where the derivative is either 0, so a smooth max or min, or undefined, so a sharp max or min, basically. And then the following hold. So there are three scenarios, basically. Either you have a local max or local min, or it's inconclusive, which I said is a possibility, because just because it's a critical number doesn't necessarily mean that there's an extrema at that point. So kind of remember that from 4.1. So here are the possibilities. Either f of c is a local max when f prime changes from positive to negative, meaning it's going from increase to decrease. That means you passed the max, good. Or f of c is a local min when f prime changes from negative to positive, meaning going down to going up at c. So that makes sense. And then f of c is neither max or min, so it's not even a local extrema, and this happens when there's no sign change. So again, we'll take a look at an example of that shortly, but I want to first get a few things out of the way. These are the first things I wanted to get out of the way. The next thing we're going to take a look at is something that will actually involve the next level of this idea, and that, of course, is concavity. So let's take a look at what that's all about right now. Right, so the concept of concavity is honestly a rather straightforward one. The only kind of issue is that there's actually different interpretations, or I guess you could say different ways of explaining it, but it's really the same idea all throughout. So this is the way I like to say, this is a more intuitive way of understanding what concavity means. So here I say a function f is either concave up or concave down. Concave up when the curve opens up in that region or interval, or concave down when the curve opens down in that region. So here I have just some random curve I made up, and I'm going to split the x-axis up into smaller intervals, a very particular choosing. So let me try to show you. So I'm going to split it up here and right about here at this point. Okay, so now there are, let me I guess do it in red. There are three intervals that I've created. This first one, this second one, and this third one. And I'm trying to be a little tricky here, but maybe I'm not actually being tricky, who knows, but I'm trying to. So here, the graph is opening up. So this is concave up, I'll write CU for concave up. Here in the second one, it's also concave up. So even though we pass a max, it doesn't actually affect the change in concave up, kind of like how with a decreasing and increasing, they did change at a max, but concavity doesn't change. Well, it can, but generally it doesn't. Anyways, here, this is concave up still. Okay. What about here? Now this opens down. So this point is actually where it changes concavity from concave up to concave down. And I said there were different interpretations, and really here's what I mean by this. Now remember, the link to connecting things to calculus is considering tangent lines. So if we consider a tangent line anywhere in the concave down region, let's say these two, or a tangent line anywhere in the concave up region, say here or here, what you notice is that for the concave up regions, the curve is entirely above the tangent line, whereas in the concave down region, the curve is entirely below any tangent line. So that's one interpretation. In fact, that's how the book really defines concavity. Here I say opens up or opens down, but that's more of like an intuitive way of describing it. It's not really mathematical, because what does it mean to open up? Well, visually you understand what it means when I point it out to you, but if I were to say all points that lie below a tangent line in that interval, that I think is maybe more mathematical, but you know, that's, I guess, maybe open to interpretation. There's also a pretty interesting observation here, and it's kind of one it's a little hard to imagine, but well, here let's take a look at what's happening as far as the tangent line goes. So here, notice the tangent line is getting, so this tangent line here versus that tangent line there, the second one is steeper than this one. And if you understand what steepness refers to as far as slope goes, it's a larger slope. So the larger your slope is, the steeper you are. So the slope is getting steeper and steeper and steeper, and then here it's getting lower and lower and lower like that. But really what's happening is we're kind of monitoring essentially how fast the slope is changing. So even though here it is, and again it's kind of hard to visualize, but even though it started going up and then it goes down now because you have a negative slope, well, actually the slope is still increasing, because here this is negative steepness, and then it'll get less steep, but the negative number actually gets larger if you think about it like that. So just to kind of give you some numbers so you can visualize that, let's say this slope is -10, then if it gets less steep it's -8 or -5 or something like that. But all that really means is the number is increasing from -10 to -5. So the slope would still be increasing. In other words, the derivative is increasing. In other words, the second derivative is positive. So that is a little hard to visualize maybe, but remember, when something is increasing, when a function is increasing, its derivative is positive. That's what we just saw. So really what we kind of are doing is looking at the function f prime opposed to f, which is, I don't want to get into it and draw that, but you can always try to discuss these things if you'd like, but I'm not going to get into that. Instead, what I'm just going to say, just to keep it simple, is this. If f double prime of x is bigger than 0, then the function is concave up in that region. If f double prime of x is less than 0, then f is concave down in that region. For the reason I said earlier, as far as how fast the derivative is changing, how fast the function is increasing. So that's basically, there's a relationship there between the second derivative and concavity, which isn't very obvious, and it's all in an explanation I said. So I may not have done that justice, but that was it. The next thing I want to talk about is a point like this, where we had a change in concavity, and this is called an inflection point. So an inflection point is just a point in the curve where there is a change in concavity. Now, as far as finding that point, it's really where you have a sign change in f double prime. So let me just say this corresponds to sign change in f double prime. And this really corresponds to how we did things with first derivative to find extrema. So extrema with first derivatives is kind of comparable to, well, points of inflection or inflection points with the second derivative. Notice, extrema is where you had a change in increase-decrease. An inflection point is where you have change in concavity. So there's a lot of parallels there. In fact, we'll see a lot of the process is really the same. But again, I'm holding up the examples till the very end so we can handle all of it at once. The last thing I want to say here is the second derivative test. We saw the first derivative test basically told us kind of what I said here, but for extrema. If you have a sign change in a particular order, you can find a max or a min, or if there's no sign change, then there is no max or min at that point. Here, the second derivative test is a little more powerful. It says that if f double prime is continuous near number c, which is of course really our critical point, our critical number I should say, and we have either f prime of c is 0 and f double prime is positive, that implies that f is a local minimum. And really what I'm saying here is, remember, if f prime of c is 0, what does that mean? That means there's a horizontal tangent line. And if f prime of c is positive, what does that mean? That means it's concave up. So if you're concave up in a region and you have a horizontal tangent line, that means that you are a minimum. You're a local minimum. Similarly, if it's f prime of 0, f prime is equal to 0, and f double prime of c is less than 0, then it's concave down at a horizontal tangent line, so it's the highest point in that region. In other words, the local max. Okay. So now we're going to take a look at some examples where we'll try to bring all of this together and hopefully get a good understanding of what the shape of the graph is looking like really. And the potential goal here is to sketch the graph, but I'm really just going to ask you for certain intervals of increase, decrease, intervals of concavity, maybe inflection points, extrema. From there, you can kind of gather what the sketch would look like. But let's take a look at those examples right now. All right, so in this example, we're given this function and we're trying to find, well, a bunch of things. Intervals of increase, decrease, local max mins or absolute maximins, intervals of concavity, inflection points, there we go, and finally sketch of the graph. So really we're going to bring all of those ideas together once we actually sketch the graph. So let's see. So just to begin, I'm going to take the first derivative of this function, and I'm going to set it equal to 0 to find critical numbers. Now notice this this derivative is a polynomial. It's, well, existent everywhere basically. There's no discontinuity, in other words, so the derivative always exists. And critical numbers are where the derivative is either 0 or doesn't exist, but since it always exists, it's only when it's equal to 0. Now we can factor out 4x squared, and what we have left over on the inside now would then just be x minus 3, I guess. So by the zero product property or zero factor property, whatever you want to call it, you either get x is 0 from this factor or x is 3 from that factor. So these are our critical numbers. And all we want to do is we want to actually check for any sign changes around these critical numbers. So to do that, what I'm going to do is I'm going to graph the x-axis with the points that we just found, 0 and 3. I'm going to test numbers around these. I'm going to plug them into f prime just to check the sign. If f prime is positive, it's increasing. If f prime is negative, it's decreasing in that region. This is basically, well, the test for increase, decrease. So to the left of 0, I'm going to test -1. In between 0 and 3, I'm going to test 1. And after 3, so to the right of 3, I'm going to test, let's say, 4. So I want to plug these into f prime. But to be quite honest, it's best to plug it into it being factored so we can just check for sign. We don't care what the number is, just what the sign of the number is. -1 squared is +1. -1 minus 3 is negative. Positive times negative will give you a negative here in this region. If you want to actually go through it and actually find the number, you can. But all I care about is that it's a negative number because that tells me that it'll be decreasing in this interval. Good. All right, now how about here when we plug in 1? Well, 1 squared is positive. 1 minus 3 is -2. So we'll have positive times negative, which is also negative. So there's no sign change here, actually. So that means that this is not a max or min by the, well, first derivative test. Remember, change in sign in the first derivative. Good. What about here? Well, if we plug in 4, we get 4 squared, that's positive. 4 minus 3 is also positive. Positive times positive is positive. So what we get from this is actually our answer for number 1, for the first part. So we actually have found now intervals of increase and intervals of decrease. So what are the intervals of increase where it's positive? So that's from 3 to infinity. Okay. Where it's decreasing, it's actually decreasing through this whole interval. There may be technicalities in writing this. In fact, you could possibly write this as negative infinity to 0, union 0 to 3, kind of like saying that at 0, it's actually not decreasing technically, it's like at a standstill. So in other words, the function will do something like this. So at this point, it doesn't really decrease. There's a horizontal tangent line there technically, but it's not a max or min, which I said, I warned you that that can possibly happen. So really the way I'm going to write this technically is I'm going to write this as negative infinity to 0 union 0 to 3. If you want to write negative infinity to 3, I guess that may be acceptable, but technically it would be incorrect because at 0 it's not really decreasing, it's horizontal tangent line. So it's kind of constant at that point. But anyways, that's just me being kind of maybe too technical. All right, so now what? Well, now the second part here is asking us for local max and mins or absolute max and mins. Because remember, extrema just means a max or a min. So I should box this, by the way. All right, good. Now remember, by the first derivative test, like I mentioned earlier, we're looking for sign changes. Here, this critical number, there's no sign change, so 0, there's no max or min. But here there is a sign change, so it is a max or a min. In fact, if it goes down, then goes up, so decreasing, then increasing, we have passed a minimum. We've passed the lowest point. So at 3, there is a minimum. So there is a local minimum. In fact, it could be a absolute minimum. I mean, if you just kind of graph based on this idea alone, so I guess I'll just kind of draw it like this. So we have these 3 points. Well, these 3, not points, but these 3 x values. So at 0, it's decreasing. Then from 0 to 3, it's also decreasing. And then here, it goes back up. So does it ever go back down? No, because, well, it says plus here only. So that means it continues to go back up. Meaning that at 3, this is actually the lowest point of the entire function, actually. Otherwise, there would be a point, well, that would be lower, meaning that it would have to increase before this, but it was only decreasing before this. Or it'd have to decrease after this, but it's only increasing after 3. So in fact, this actually is an absolute minimum, not a local minimum. And that absolute minimum is at x equals 3. Now the actual number that it is f of 3. So we have to plug this into the original function. So that's going to be 3 to the 4th, which is 81, minus 4 times, well, 3 to the 3rd is 27. And let's see, what's 4 times 27? So that's going to be 108, I think. So 81 minus 108, that's actually going to be negative 27. So that makes sense because it looks like it's negative here, but that was me kind of assuming that it would be like this. It could have been above the x-axis. But anyways, it is negative 27. So this actually is our only extrema, local or absolute. So we actually only have one absolute min. Strange. Right, so now, well, we're done with steps 1 and 2. Now for the third part, we're trying to find intervals of concavity, concave up or concave down. So with that being said, we're going to repeat this same thing we just did, but now with the second derivative. So now we're done with all this. Now we're going to kind of repeat this, but with the second derivative now. So if f prime is, before we factor, that way we don't have to use a product rule, 4x cubed minus 12x squared, the derivative of that will be 12x squared, okay, minus 2 times 12 is 24x. Now I want to set this equal to 0 to find out potential points where we have inflection points. Okay, good. So now I'm going to, let's see, I'm going to solve this by factoring out 12x in this case. And when you factor out 12x, you have x minus 2 on the inside. So by the zero factor property or zero product property, whatever you want to call it, either this is 0 or this is 0, meaning x is either 0 or positive 2. So now what we're going to do is the same exact thing we did here with the first derivative, but now with the second derivative. So we're going to plot these points, 0 and 2, on the x-axis. We are going to test numbers around them, and we're going to see if the second derivative is either positive or negative in that region. Good. So what do you want to test? I'm going to test negative 1, 1, and 3. And I want to do it into the factored version of the second derivative, so it's easier to check for sign. So negative 1 times 12, that's negative. Negative 1 minus 2 is negative 3. Negative times negative is positive. Good. Here, if you plug in 1, 1 times 12 is positive. 1 minus 2 is negative. Positive times negative is negative. And here, if you plug in 3, you get 12 times 3, that's positive. 3 minus 2 is positive. Positive times positive is positive. Good. So what we've discovered from this is, remember the test for concavity that I kind of mentioned to you earlier. When the second derivative is positive, it's concave up. Where the second derivative is negative, it's concave down. So for our interval of concave up, we have the pluses. So negative infinity to 0. Union, the other one, 2 to infinity. Where it's concave down, however, is where it's negative, and it's negative in this interval 0 to 2. Perfect. Great. So we've done the first 3 parts, and the fourth part is kind of simple actually. We're just looking for sign changes of the second derivative, just like we did for the local max and local min. But it's kind of better because a point of concavity is a little more particular, and extrema isn't. Well, I guess it's the opposite way. So extrema is more particular because there are different names for extrema. Either it's a max, or there's a min, or it's a min, or it's local, or it's absolute. An inflection point is just an inflection point. You don't have to see if it went up and went down, or if it changed from concave up to concave down, or vice versa. It doesn't really matter. So all I'm going to do is check where there's a sign change, and that's at both of these, 0 and a 2. Also, the difference here is the language. So an inflection point is legitimately just a point. So for the inflection points, we know there's 2 of them, and one of them is 0 comma something, and the other one is 2 comma something. So all I'm doing is grabbing these x values we got where there's sign change in the second derivative, plugging it into the original function. So notice 0 to the fourth minus 4 times 0 cubed is still 0, so that's one of them. And when you plug in 2, let's see, you get 2 to the fourth, which is 16, minus 4 times 2 to the third, that's 4 times 8, by the way. So that's 16 minus 32, that's negative 16. So at these 2 points here, there is a change in concavity. And now finally for step 5, can we sketch the graph from all of this? I think we can. I'm going to try anyways. It may not be to scale, but there are a few points we care about. So notice, well, I guess we can take a look at just these ones here. So the main x values we care about are 0, 2, and 3. So 0, 1, 2, 3, and let's just say 4 just for consistency. Now, what about y values? What y values do we care about? It looks like the only real y values that come to play are 0, 0, well, I guess 0, so negative 16, and the only other y value is a negative 27. So 2 comma negative 16, let's just say, is down here, and 3 comma negative 27, even though it's not too much to scale, let's just say it's down here. Okay, good. So now what's happening from negative infinity to 0? The function's going down, but it passes through 0, 0. And from negative infinity to 0, it's concave up. So the function has to look like this. It opens up but goes down. Great. From 0 to 2, it's concave down now, so there's a change in concavity. And and it passes through the point 2 comma negative 16. So this would be it being concave down. Good. Now at this point, there's a change in concavity, so now instead of concave down, from 2 to infinity, now it's all concave up. And at 3 comma negative 27, there's a minimum. So let's just say this is the point here. So now it's concave up, and then it continues to be concave up. Now I'm not super precise on where it actually passes through the x-axis. We could actually find the x-intercepts. Well, it actually is at 4, you can see that. Because if you pull out x to the third, you have x to the third times x minus 4, and when x minus 4 is 0, that means x is 0. So really, to be a little more specific on the graph, I should have realized that ahead of time. But that's good, that's okay. So this is actually a pretty precise image of what the graph looks like. And of course, you can graph this by yourself on a graphing utility, but we definitely see all the key features here. Intervals of increase, intervals of decrease, absolute minimum in this case, concave up, concave down, concave up, inflection points, and that's basically about it. So nice, pretty decent sketch of the graph just based on calculus. So I don't know if the video is getting kind of long, but I want to show you one more example where I'm going to do the same exact thing we did here. I'm going to try to do a little quicker though. It's going to be a little more complicated than the example, so I don't know how much quicker we'll be able to go through the problem, but I still think we deserve to see at least one more problem. So let's take a look at that example right now. Right, so this example is a little more complicated than the previous one. In fact, here we need product rule to even get the ball rolling as far as first derivative goes. There is kind of a way to avoid product rule. If you recognize that x is the same as radical x squared, you can distribute x squared in and get the square root of x to the, well, 6x squared minus x to the third. And notice square root is really 1/2 power. So you can find the first derivative this way by using chain rule. Let me do that, and I'll kind of show you. So let's see. So if we use this with chain rule, derivative of this is 1/2 the inside to the negative 1/2 times derivative of the inside. Derivative of the inside, of course, is 12x minus 3x squared. And there's a lot we can actually get from this. Let's see. First off, we can pull x squared out of the 1/2 power, but it's in the denominator now. So just to kind of clean this image up a little bit, well, let's see, it's over 2 because of the 1/2. This was to the 1/2, which we know is square root. So I guess we could leave it like that. But we notice that they both have x squared in common. When you pull x squared out of the radical, it comes out as x. So we really just have 6 minus x inside the radical. Here, these two actually, you can pull out 3x on top, because there's no negative exponent, so it's in the numerator technically. And what you have left over after pulling that out would be, I guess, 4 minus x. Good? Great. So there was a lot of messing around there. We get this, and of course you notice the x's cancel. So really this is just 3 times 4 minus x over 2 times the square root of 6 minus x. Which is great because we can find critical numbers where the top and bottom are each equal to 0. So of course our critical numbers here are x equals, so let me just write critical numbers here, are x equals 4 from the top and 6 from the bottom. There's kind of a problem with 6. Well, we'll see, because remember the next step now is to plot them on the real number line and test numbers around those. So we have 4 and 6 like this. And let's see what we want to test, and once we realize what we want to test, we'll actually come to the realization of why 6 is a little funny. So we can plug in, let's say, 3, 5, and you're probably thinking 7 here. Now, once you actually start to plug them in, there's a problem with plugging in 7. And the problem with plugging in 7 is that you'll get 6 minus 7 in the radical, which is negative. In fact, I could tell right away that that would happen because the original function has 6 minus x, meaning that any number larger than 6 would not be in the domain. So in fact, something pretty important, I think, is to consider domains. So far, we only saw one example before this, though, and that example had a domain of negative infinity to infinity, which is kind of typical in these types of problems. But here I wanted to do this one because it doesn't have that domain. So here the domain is actually negative infinity to 6, closed on 6. So plugging in any other numbers besides these, in other words, numbers greater than 6 will cause an issue, will have a negative inside of a radical. So this is bad news, because in that area there's like nothing going on with the graph. Okay, so we can plug these numbers in, we can test for the first derivative, and let's see what happens. All right, so again, we want to plug into the factored version of f prime, and we're going to check for sign only. So on the top, we have 4 minus 3 is positive. On the bottom, well, 6 minus 3 is positive. You'll always have a positive inside the radical. So this is positive over positive, which is positive. When you plug in 5, however, you get 4 minus 5 on the top, which is negative, and again, 6 minus 5 inside the radical is always going to be positive. So it's negative over positive, which is negative. So for part 1 of our question, we have increasing in the interval negative infinity to 4 and decreasing in the interval 4 to 6. And by the way, I may not have mentioned this before, but intervals of increase, decrease are always open. Okay. All right. Good, so now what? Well, now I guess we have to find out any sign changes of the first derivative, and that's of course at 4. It goes from, let's see, going up to going down, because increase, decrease, so that means we passed a local max. In fact, maybe it's absolute, but first let's figure out how to call it. So it's at x equals 4. And the actual value of the max will be the value that you get when you plug this into the original, and that's going to be 4 radical 2, because 6 minus 4 is 2. That's 4 radical 2. And I can actually tell that this is indeed an absolute max. And you can tell because there's no other point that's higher than this point, because of the nature of increasing and decreasing. You can't go back up to get beyond being higher than this one, and you would have had to be decreasing before this, but you're only increasing here and only decreasing here. So it's something to consider, but this is the only way that would happen. So it has to be absolute max in this case. Perfect. And now finally, for parts 3 and parts 4, we have to consider now the second derivative. So just like the first derivative took a little bit of time because it was a lot to look at, and we actually avoided doing product rule. If you use product rule, it's a little more finessing, but you should still get this in the end, or there's a way to get this in the end anyways. But now at this point, there's really no way around it. We have to use quotient rule to find the derivative of this. So instead of me kind of scrambling for room here, I'm going to erase this and do that now. All right, here, so I've written our result from the first derivative from what we had previously, but I've written the radical in the bottom as 1/2 power because that's better for us with derivatives. So now what? Well, now I'm going to find the second derivative, and that will incorporate using the quotient rule, which will be all over the bottom squared. 2 squared is 4, and the radical squared is just the inside. So notice taking something to the 1/2 to the second cancels the powers, and you just get this in the end. Now, for the numerator of the quotient rule, we need to do derivative of the top, which is 3 times -1, because the derivative of 4 minus x is 0 minus 1, times regular of the bottom, so that's 2, and then 6 minus x to the 1/2. Hope we have space here. Minus regular of the top, 3 times 4 minus x, times derivative of the bottom. Now for derivative of the bottom, if we bring the 1/2 down using power rule, they cancel with the 2 here. So we end up just getting 6 minus x to the inside to the negative 1/2 power, but then by the chain rule, we have to multiply by derivative of the inside, which is -1. But the -1, I'm not going to write it because it's just going to cancel this sign and make it positive. Whew, nice. So we have this, good. Now what can we do? There's actually quite a bit we can do. I'm going to multiply the top by 6, well, top and bottom, by 6 minus x to the 1/2. So if you multiply top and bottom by 6 minus x to the 1/2, you'll kind of see why we need to do that. It'll get rid of this radical in the top for the first term, because if you distribute this, 1/2 plus 1/2 is 1. And here it'll get rid of this negative power because it cancels out. So let's see if we can bring that all together now. So now at the bottom we have 4, 6 minus x to the 1 plus 1/2 is 3/2. Good. Here, this combined, well, really this is just -6. 3 times -1 times 2 is -6. So that's 6 minus x to the, well, 1/2 plus 1/2 is just 1, so there's no power to write really. And then plus 3 times 4 minus x, and no other factor because distributing this in here will cancel this factor. So now if we distribute this and this, let's see finally what we get in the top. We get -36 plus 6x plus 12 minus 3x, all over 4 times 6 minus x to the 3/2. And that simplifies pretty tremendously. 6 minus 3x, 6x minus 3x is 3x. And -36 plus 12 is -24. And there's nothing really we can cancel out, but we can definitely factor 3 from the top. So we get x minus 8 in that set of parentheses there. Perfect. So it's looking pretty good, and from this we can actually tell what the critical numbers would be. Really, they're not called critical numbers here because now we're dealing with the second derivative opposed to the first. So those numbers I'm talking about, of course, are 8 and 6 because that's when each of these factors are equal to 0. So we're going to plot those numbers on a number line, but just for space, just in case, I'm going to erase this, but just write the result up here. Right, great. So like I said, when you set the top equal to 0, you get x is equal to 8. When you set the bottom equal to 0, you end up getting this factor on the inside being equal to 0, which will give us x is equal to 6. So let me just write that here. X is equal to 8 or 6. So now let's plot those on the number line. But again, there's a problem with 8. The problem with 8 is it's not actually in the domain. Notice when you plug in 8, you get 6 minus 8, which is negative inside the radical. So nothing over here actually exists. So really, all of this region is either concave up or concave down. And with that being said, there are actually no inflection points, which is kind of funny. So there's no change in concavity. It's always the same concavity, concave up or concave down. And we can pick any number, less than 6. So let's plug in 0, just for the sake of simplicity, I guess. So we're going to test 0 in for the second derivative, and we're just checking for the sign. On the top, we'll get negative because we'll have a 0 minus 8. On the bottom, 6 minus 0 is positive. Negative over positive is negative. So that means this is always concave down. So it's actually concave down in the entire domain of f, which is negative infinity to 6. Intervals of concavity, just like intervals of increase-decrease, are always open. So that's okay. And inflection points, unfortunately, they do not exist. There aren't any. And can we bring all of this together to actually find the sketch of the graph? Believe we can. Let's see if we can do it. So what are the main points I want to focus on here? Well, we have x equals 4. X equals 6 is coming up a lot, kind of. And I thought I had 0, but I guess we don't actually have 0. I mean, what's nice is that when you plug in 0, you get 0 anyways, because it's 0 times radical 6, which is 0. So just because it's a nice point, the x and y intercept, actually, I'm going to plot that point 0, 0. And then we have, let's see, 1, 2, 3, 4, and 5, and 6. So at 6 is where the function ends because the domain of the function is negative infinity to 6 only. So let's see, it's increasing from negative infinity to 4, so it's going down. At 4, there is an absolute maximum. I'm sorry, it's going up because negative infinity to 4 is an interval of increasing, my mistake. And it's absolute max, and that's at 4 radical 2. So let's say 4 radical 2 is here. I don't know exactly what the number is, but you can approximate that if you want. And we get something like this. So it's increasing even before this point, so it's going up like that. And it's actually always concave down. So it's going to look like this, actually. So even though I've emphasized on this point, there's nothing funny happening at this point. It's just like a straight through action like that. Great. And now what about between 4 and 6? Well, between 4 and 6 it's decreasing, and remember, it's still concave down. And actually, we can plug in 6, I haven't done that yet, but we get 6 times, well, 6 minus 6 in the radical is 0, so that's our other x-intercept actually. And we get this type of image here. Perfect. So from all of this is the sketch of the graph. And again, you can graph to compare on your own. And again, we only did 2 examples in this section, but I felt like it's enough. We saw a lot of different things going on. So I hope that made sense to you. Hope it was clear. Hope we enjoyed this section. I'll see you in the next videos for the rest of chapter 4. It's going to be pretty interesting, actually. And thanks for watching. See you then.